What if I told you there's a place in the universe where a single teaspoon of matter weighs as much as 1,000 elephants? Sounds impossible, right? Yet out there in the cosmos, reality bends to extremes that defy everything we know. Welcome to the bizarre and breathtaking world of cosmic densities, where space folds in on itself, matter gets crushed beyond recognition, and the laws of physics as we understand them simply break. From the heart of collapsed stars to the invisible monsters lurking in the void, the universe hides pockets of such incredible density that they warp time, light, and even our understanding of existence itself. Density might sound like a dry scientific term, a simple ratio of mass to volume, but in the grand theater of space, it becomes a spectacle of violence and wonder. Picture this: a star 20 times heavier than our Sun, squeezed into a ball no wider than Manhattan, or a black hole so dense that not even light can escape its grasp. These aren't just theoretical curiosities, they're real, lurking in the darkness, reshaping galaxies and challenging everything we thought we knew about matter. And here's the wildest part: these extremes aren't rare. They're woven into the fabric of the cosmos, hiding in plain sight, waiting to be uncovered. So why should we care? Because these cosmic heavyweights hold the keys to some of the universe's greatest mysteries. They're the engines behind the brightest explosions, the architects of gravity's most dramatic performances, and maybe even the doorway to realms of physics we've yet to dream of. Over the next 30 mind-expanding facts, we'll venture into the crushingly dense heart of neutron stars, unravel the secrets of quasars brighter than 1,000,000,000,000 suns, and confront the terrifying beauty of singularities, where density becomes infinite and reality as we know it just stops. Buckle up, this isn't just a tour of space's oddities, it's a journey to the edge of what's possible. Among the most extreme objects in the universe, neutron stars stand as cosmic anomalies where matter is packed so tightly it defies comprehension. Imagine taking a star 10 times more massive than our Sun and crushing it down into a sphere the size of a city. The result, a neutron star where gravity has won an unimaginable battle, squeezing atoms until they collapse into a sea of neutrons. Just a single teaspoon of this ultra-dense material would weigh around 1 billion tons on Earth. That's like compressing Mount Everest into a sugar cube. How does something so extreme form? It all begins with a supernova, one of the most violent events in the cosmos. When a massive star runs out of fuel, its core collapses under its own weight in a fraction of a second. The outer layers explode outward in a blinding flash, while the core, now compressed beyond recognition, becomes a neutron star. This leftover remnant spins at dizzying speeds, some rotating hundreds of times per second, sending out beams of radiation that we detect as pulsars. But the real mind-bender is the gravity. Stand on the surface of a neutron star, and the pull would be 100 billion times stronger than Earth. It's so intense that even the shape of atoms gets distorted, flattening into spaghetti-like strands. Even light itself bends under this force. If you could hover above the surface, you'd see the back of your own head as gravity warps light into a full circle. These cosmic powerhouses don't just sit quietly. Neutron stars can unleash bursts of energy so violent that they momentarily outshine entire galaxies. Some, locked in deadly dances with companion stars, siphon off material until they erupt in titanic X-ray explosions. Others collide in catastrophic mergers, sending ripples through spacetime itself, events so powerful they literally shake the universe. Yet for all their ferocity, neutron stars are also cosmic laboratories. Inside, conditions resemble those just moments after the Big Bang, letting us glimpse physics at its most extreme. They might even hold clues to the nature of dark matter, the mysteries of quantum forces, and whether there's something even denser lurking in the cosmos. One thing's certain: these stellar remnants prove that when it comes to the universe, the most unimaginable realities often turn out to be true. If neutron stars are cosmic anomalies, pulsars are their high-performance cousins, nature's ultimate precision instruments. These rapidly spinning stellar corpses can complete hundreds of rotations every second, flashing beams of radiation across the universe with clockwork regularity. Picture a lighthouse on a cosmic scale, but instead of light, it emits focused jets of X-rays or radio waves, sweeping past Earth like the hands of a hyperactive stopwatch. First discovered in 1967 by astronomer Jocelyn Bell Burnell, these pulses were so unnervingly precise that scientists briefly nicknamed them LGM for Little Green Men, wondering if they'd stumbled upon an alien transmission. The secret to their mesmerizing spin lies in the physics of collapse. When a massive star implodes into a neutron star, it conserves its original angular momentum, but squeezed into a tiny package, that spin becomes ferociously amplified. It's like an Olympic figure skater pulling their arms in to accelerate a dizzying pirouette, except here, the skater is a city-sized object spinning faster than a kitchen blender. Some pulsars, known as millisecond pulsars, reach speeds exceeding 700 rotations per second, so fast that their surfaces move at nearly a quarter the speed of light. But what truly sets pulsars apart is their eerie reliability. Their beams sweep past Earth with such predictability that they rival atomic clocks in accuracy. Astronomers have used them to test Einstein's theory of relativity with exquisite precision, observing how their pulses slow when passing through warped spacetime near massive objects. They've even become interstellar navigation beacons. NASA, a Voyager spacecraft, carry pulsar maps just in case future civilizations or curious aliens need to locate Earth. Yet for all their stability, pulsars aren't gentle giants. Their magnetic fields are 1 trillion times stronger than Earth's, powerful enough to rip apart atoms from thousands of miles away. Some, called magnetars, take this brutality further, occasionally unleashing starquakes so violent they momentarily outshine the Milky Way. Others, locked in binary systems, gradually devour their companion stars, spinning ever faster as they feed cosmic vampires growing more frenetic with every bite. These spinning sentinels aren't just astrophysical curiosities, they're time capsules and natural laboratories. By studying their pulses, scientists have uncovered planets in orbit around them, detected the faint whispers of gravitational waves, and probed the mysterious state of matter at densities beyond anything we can recreate. They remind us that even in death, stars continue to shape the universe, not just as silent remnants, but as beacons, clocks, and engines of extreme physics. Black holes take cosmic density to its ultimate extreme, a point where the rules of physics as we know them cease to exist. At their heart lies the singularity, a region of infinite density where matter is crushed into a mathematical paradox. Imagine compressing the entire mass of a star or even a galaxy into a single point with zero volume. The gravitational pull becomes so intense that not even light can escape once it crosses the event horizon, the point of no return. This boundary isn't a physical surface but a threshold where the universe itself bends to the black hole's will, warping spacetime so severely that time slows to a crawl for anyone unfortunate enough to approach it. The event horizon acts like a one-way door. Once something passes through, there's no coming back, but the true enigma lies deeper. The singularity defies all known laws, a place where density becomes infinite and Einstein's equations break down. Here, quantum mechanics and general relativity collide in a cosmic showdown, exposing the limits of our understanding. Some theories suggest singularities might be gateways to other universes or dimensions, while others propose they simply erase everything that enters, leaving no trace behind. Black holes don't just distort space, they twist time itself. Near the event horizon, gravitational time dilation means an observer watching from a safe distance would see a falling object slow to a standstill, frozen in time as the black hole's pull stretches seconds into eternity. Meanwhile, the unlucky traveler would experience something far more horrifying: spaghettification, where tidal forces stretch them into a thin, noodle-like strand before obliterating them completely. These cosmic monsters come in different sizes, from stellar mass black holes born from collapsing stars to supermassive behemoths lurking at the centers of galaxies. The largest, like Sagittarius, a star at the heart of the Milky Way, weigh millions of times more than our Sun. Yet despite their terrifying reputation, black holes aren't just destructive, they shape the cosmos. Their immense gravity can forge entire galaxies, funneling matter into swirling disks that glow brighter than 1 trillion suns. Jets of particles shoot from their poles at near light speed, carving out vast structures in intergalactic space. Studying black holes pushes the boundaries of human knowledge, forcing us to confront the most fundamental questions about space, time, and the nature of reality itself. They're not just cosmic oddities, they're the universe's way of showing us how strange, violent, and awe-inspiring existence can truly be. Beyond neutron stars, the universe might harbor something even stranger: objects so dense they blur the line between star and singularity. Meet quark stars, hypothetical cosmic powerhouses where matter doesn't just compress, it dissolves into its most fundamental building blocks. Picture a neutron star pushed past its breaking point, its crushing gravity overwhelming even the sturdy neutrons, forcing them to crumble into a seething soup of quarks and gluons. This is quark matter, a state so extreme it hasn't existed naturally since the first microseconds after the Big Bang. Quark stars, if they exist, would be the ultimate pressure cookers. While neutron stars squeeze atoms into a sea of neutrons, quark stars take it a step further, breaking those neutrons apart until only their constituent quarks remain, swimming in a roiling plasma. The density here defies imagination. A single sugar cube's worth could outweigh every skyscraper on Earth combined. But unlike black holes, quark stars might still have a surface, a thin crust of ultra-dense material shielding the chaotic quark ocean beneath. Why haven't we found one yet? The challenge lies in their disguise. Quark stars could masquerade as neutron stars with nearly identical sizes and temperatures. The telltale clues would be subtle, slightly smaller radii, unusually high energy emissions, or freakishly fast spins pushed beyond what neutron stars should sustain. Some astronomers suspect a few known neutron stars, like the mysteriously massive object at the heart of supernova remnant 358, might actually be quark stars in hiding. Others hunt for their signatures in the gravitational waves released when dense objects collide, listening for the unique ringing a quark star would produce. Theorists argue these objects could form when a neutron star gains too much mass, perhaps by devouring a companion or merging with another. At a critical threshold, the neutrons surrender, dissolving into quarks like sand collapsing under a tidal wave. Some models even suggest quark stars could be the true ancestors of certain black holes, a fleeting intermediate state before gravity wins completely. Discovering a quark star would rewrite textbooks. It'd prove that matter can exist in a state thought impossible outside particle colliders, offering a window into the universe's earliest moments. These bizarre objects might also explain extreme cosmic explosions like superluminous supernova, whose energy defies conventional models. For now, quark stars remain ghosts in the equations, but if they're out there lurking in the dark, they could be the ultimate key to understanding how matter behaves when pushed to the very brink of existence. White dwarfs are the ghostly embers of stars like our Sun. Stellar remnants so dense that a teaspoon of their material would weigh as much as an elephant. These Earth-sized cinders pack the mass of an entire star into a volume smaller than some asteroids, creating gravitational forces 100,000 times stronger than what we experience on Earth. When a Sun-like star exhausts its nuclear fuel, it sheds its outer layers in a shimmering planetary nebula, leaving behind only its scorched core. This core, no longer fueled by fusion, collapses under its own weight until the electrons inside are pressed shoulder to shoulder in a bizarre quantum state called degenerate matter. What does that mean? Normally, electrons repel each other, keeping atoms apart. But in a white dwarf, gravity wins that battle, squeezing electrons so tightly they can't compress further without violating quantum laws. The result is a star that glows faintly from residual heat, cooling over billions of years like a forgotten ember in a cosmic fireplace. Some white dwarfs, though, refuse to fade quietly. In binary systems, they can siphon material from a companion star, igniting runaway nuclear reactions on their surfaces that trigger cataclysmic explosions, nova so bright they're visible across galaxies. The most massive white dwarfs flirt with disaster, approach a critical limit about 1.4 times the Sun's mass, and electron degeneracy pressure can no longer hold back gravity. The star collapses further, either detonating in a thermonuclear supernova or crushing itself into a neutron star. Yet even ordinary white dwarfs defy intuition. Their intense gravity bends light so severely that if you could stand on one, which you couldn't, since you'd be instantly flattened, you'd see the entire universe warped into a circular panorama around you. These stellar relics aren't just cosmic curiosities. They're timekeepers, cooling at predictable rates that let astronomers estimate the age of their surrounding galaxies. Some even harbor crystallized cores, their carbon atoms frozen into diamond-like structures over eons. And occasionally, they surprise us like the white dwarf that somehow survived its own supernova, or the one with an oxygen atmosphere defying all expectations. White dwarfs remind us that even in death, stars continue to shape the universe, leaving behind cryptic clues written in density, light, and the unyielding laws of physics. While stellar black holes are born from the explosive deaths of massive stars, their supermassive cousins operate on an entirely different scale, cosmic behemoths with appetites that defy logic. Take Sagittarius, a star, the monster lurking at the center of our Milky Way. This gravitational titan weighs 4 million times more than our Sun, yet it's crammed into a space no larger than our solar system. But here's the paradox: despite their unimaginable mass, supermassive black holes are technically less dense than water. How? Because density depends on volume, and these giants have so much room to spread out their mass that, on average, they're surprisingly fluffy. Their formation remains one of astrophysics' greatest puzzles. Did they grow from stellar black holes gorging on gas and stars for billions of years? Or were they born already massive from the collapse of primordial gas clouds in the early universe? Some might even have formed from direct collapsing dark matter, skipping the star stage entirely. What we do know is their influence is unparalleled. These invisible giants sculpt entire galaxies, their gravitational pull orchestrating the motion of stars like cosmic conductors. Without them, galaxies like ours might never have formed. Their immense gravity acts as an anchor, drawing in gas and dust to fuel star birth while simultaneously regulating galactic growth. But don't let their low density fool you. Near the event horizon, spacetime warps into a nightmare vortex. Stars unfortunate enough to wander too close get stretched into luminous spaghetti strands, their material swirling into an accretion disk hot enough to outshine every star in the galaxy combined. Some supermassive black holes, like the one powering quasar-ton 618, devour matter so voraciously their disks glow with the brightness of 100 trillion suns visible across more than half the observable universe. Yet these monsters aren't just destroyers. Their relativistic jets, spewing particles at near light speed, carve out vast bubbles in intergalactic space, seeding future star formation. They might even hold clues to the universe's fate. Will they eventually consume everything or fade away over trillions of years as Hawking radiation slowly evaporates them? One thing's certain: supermassive black holes are the universe's ultimate paradoxes, simultaneously the least dense and most dominant objects in existence, proving that when it comes to cosmic extremes, reality always finds a way to surprise us. At the heart of our solar system, buried beneath hundreds of thousands of miles of searing plasma, lies the Sun's core, a cosmic pressure cooker where nature performs its most spectacular alchemy. Here, under pressures 250 billion times stronger than Earth's atmosphere, hydrogen atoms are squeezed so tightly they fuse into helium, unleashing the energy that sustains life across our planet. The core may only occupy about 1/50th of the Sun's total volume, but it's where 99% of its energy originates, packed into a region so dense that a single cubic centimeter, the size of a sugar cube, contains over 150 grams of matter. That's 15 times denser than lead, compressed under conditions hotter than 15 million degrees Celsius. What keeps this inferno from exploding outward? The Sun's own immense gravity. Every second, 600 million tons of hydrogen fuse into helium, yet the core's crushing weight ensures this energy releases gradually, like a valve controlling a cosmic steam engine. Without this balance, our star would either collapse under its own weight or detonate like a titanic bomb. Instead, it hums along with eerie stability, converting matter into energy with the efficiency of a nuclear power plant the size of 1,000,000 Earths. The numbers defy comprehension. The energy produced in the core equals 100 billion 1-megaton nuclear bombs detonating every second. Yet it takes photons thousands of years to fight their way through the Sun's dense layers before finally escaping as sunlight. By contrast, the neutrinos born in these reactions streak through space almost unimpeded, offering scientists ghostly fingerprints of the core's hidden workings. This furnace doesn't just power the solar system, it's our closest laboratory for extreme physics. Conditions here mimic those inside hydrogen bombs and experimental fusion reactors, yet nature sustains them effortlessly for billions of years. As we unravel the Sun's secrets, from the quantum dance of proton collisions to the way it subtly vibrates like a colossal gong, we're reminded that the most ordinary-looking star in our sky harbors one of the universe's most extraordinary engines. And every ray of sunshine that touches your skin is the ancient echo of atomic fire, born in a place where density and energy reign supreme. Before stars, before galaxies, before even atoms existed, the newborn universe was a churning ocean of pure energy. Imagine a space so hot and dense that the fundamental particles we consider indestructible today couldn't even hold themselves together. This was the quark-gluon plasma, the universe's first state of matter, existing just microseconds after the Big Bang when temperatures exceeded trillions of degrees. In this primordial soup, quarks and gluons, the building blocks of protons and neutrons, roamed freely, unbound by the nuclear forces that would later glue them together. It's a state of matter so extreme that even the insides of neutron stars seem orderly by comparison. The transformation from this chaotic plasma to the structured universe we know is one of nature's most breathtaking metamorphoses. As the universe expanded and cooled, the energy density dropped dramatically. Around 1 microsecond after the Big Bang, the temperature fell enough for quarks and gluons to finally freeze into composite particles, protons and neutrons. This process, called hadronization, was like watching a superheated gas suddenly condense into droplets. But the universe wasn't done cooking. For the next few minutes, it became a nuclear fusion reactor, with protons and neutrons colliding to form the first atomic nuclei, mostly hydrogen and helium, with traces of lithium. Here's where it gets even wilder. For nearly 400,000 years, the universe remained too hot for electrons to settle into orbit around these nuclei. Space was an opaque fog of ionized particles, scattering light relentlessly. Only when temperatures dropped to around 3000 Kelvin, comparable to a red dwarf star's surface today, could electrons finally combine with nuclei to form neutral atoms. This moment, called recombination, cleared the cosmic fog, allowing photons to travel freely for the first time. Those ancient photons are still detectable today as the cosmic microwave background, the afterglow of the Big Bang. Scientists recreate fleeting glimpses of this primordial plasma in particle colliders like the Large Hadron Collider. By smashing heavy ions together at nearly light speed, they generate microscopic fireballs that mimic the early universe's conditions for mere fractions of a second. These experiments reveal a startling truth. Quark-gluon plasma behaves more like a perfect liquid than a gas, flowing with almost zero friction despite its unimaginable density. The echoes of this violent beginning are everywhere. The ratio of hydrogen to helium in today's universe, a direct relic of those first few minutes, the large-scale structure of galaxies. Sculpted by density fluctuations in that ancient plasma, even the atoms in your body were forged in this cosmic crucible, their protons once participants in the universe's most extreme density experiment. The quark-gluon plasma era may have lasted barely an eye blink in cosmic terms, but its fingerprints are etched into the fabric of reality itself. The universe holds a haunting secret, a ghostly presence that outweighs all the stars, galaxies, and cosmic dust we can see. Dark matter, invisible and intangible, exerts a gravitational grip so strong it bends entire galaxy clusters like cosmic puppets. We can't touch it, shine light on it, or trap it in any detector, yet its fingerprints are everywhere. Take the Bullet Cluster, where two galaxies collided, leaving their visible gas clouds stranded while dark matter, revealed only by the way it warps light, marched straight through the wreckage like an unstoppable phantom army. What makes dark matter so baffling is its composition. It isn't made of protons, neutrons, or any known particles, otherwise we'd have detected it by now. Some theories suggest weakly interacting massive particles, or WIMP, that barely acknowledge ordinary matter's existence. Others propose actions, ultra-light particles streaming through space like an undetectable breeze. Then there's the wild card, primordial black holes, forged in the universe's first chaotic moments, lurking unseen. Whatever it is, dark matter doesn't just exist, it dominates, making up 85% of all matter in the cosmos. Here's where density gets strange. While dark matter outweighs visible matter 5 to 1, it's also more diffuse, spread out in vast halos enveloping galaxies. But in certain regions, like the cores of dwarf galaxies, it's densely packed enough to bend light into eerie rings and arcs, a phenomenon called gravitational lensing. Some simulations even suggest dark matter might form intricate structures, cosmic filaments and knots, creating an invisible skeleton upon which galaxies assemble like dew on a spider's web. Why does it refuse to interact with light or matter? The leading theory points to something beyond the standard model of physics, a shadow realm of particles governed by unknown forces. Experiments like the Large Underground Xenon Detector hunt for rare collisions between dark matter and ordinary atoms, while the Hubble telescope maps its distribution by tracing the distorted shapes of background galaxies. So far, the hunt has turned up empty, deepening the mystery. Yet without dark matter, the universe wouldn't exist as we know it. In the early cosmos, its gravitational pull gathered hydrogen gas into clumps, allowing stars to ignite. Without it, galaxies would spin themselves apart, their visible matter insufficient to hold them together. Even now, dark matter guides the universe's expansion, shaping the fate of everything. The greatest cosmic riddle isn't some distant phenomenon, it's the invisible scaffolding holding reality together, hiding in plain sight. Imagine a metropolis where stars outnumber people, a glittering cityscape spanning light years, where gravity choreographs the tightest cosmic dance imaginable. Hypercompact star clusters are the universe's ultimate urban sprawl, packing hundreds of thousands of ancient suns into a space smaller than the distance between our sun and its nearest stellar neighbor. In these dense stellar cities, stars orbit mere light weeks apart, creating gravitational mayhem where close encounters are inevitable and collisions aren't just possible, they're practically guaranteed. These clusters are cosmic relics, some nearly as old as the universe itself. Born in the chaotic early universe when gas clouds collapsed with unprecedented fervor, they've survived for billions of years, drifting through galaxies like celestial time capsules. Unlike loose open clusters where stars gradually disperse, hypercompact clusters are held together by sheer gravitational might. Their cores are so packed that if you stood on a hypothetical planet there, the night sky would blaze with thousands of stars brighter than Venus, some so close they'd visibly move across the heavens in real time. The dynamics here defy imagination. Stars don't just orbit, they slingshot around one another in chaotic gravitational exchanges, flinging some outward while dragging others deeper into the cluster's crushing core. The fastest, known as blue stragglers, steal mass from neighbors or collide outright, reigniting nuclear fusion and making them appear bizarrely youthful compared to their ancient surroundings. Meanwhile, black holes and neutron stars lurk invisibly in the crowd, their presence betrayed only by the way they yank nearby stars into erratic orbits. What's truly astonishing is how these clusters shape their surroundings. Their collective gravity can strip gas from passing galaxies, and their dense cores act like cosmic particle accelerators, hurling stars into intergalactic space at staggering speeds. Some even harbor intermediate mass black holes at their hearts, mysterious objects weighing thousands of suns, possibly formed from runaway stellar mergers. Yet for all their violence, hypercompact clusters are also stunningly beautiful. Through telescopes, they resemble delicate snow globes of light, their stars so densely packed that the core appears almost solid. They're living museums of stellar evolution, where red giants, white dwarfs, and newborn blue stragglers coexist in a snapshot of cosmic time. And they might hold clues to how the first galaxies formed, offering a glimpse into an era when the universe was young, raw, and unimaginably dense. Every star has a breaking point, a moment when the cosmic scales tip from stability to catastrophe. For a white dwarf, that threshold is 1.4 times the mass of our Sun, known as the Chandrasekhar limit. Cross this invisible line, and the delicate quantum balancing act holding the star together fails spectacularly, triggering one of the most violent events in the universe. Named after the visionary astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930, this limit isn't just a number, it's a cosmic verdict separating fading embers from total annihilation. What makes this limit so unforgiving? Inside a white dwarf, electrons are packed shoulder to shoulder, their quantum properties generating enough pressure to counteract gravity's relentless crush. But add more mass, say, by siphoning gas from a companion star, and the pressure reaches a critical point. Electrons can't resist any longer, forced to merge with protons in a process called inverse beta decay. The star's core collapses in milliseconds, temperatures skyrocket past 1 billion degrees, and a runaway nuclear fusion reaction rips through the carbon and oxygen like wildfire. The result, a Type Ia supernova, an explosion so uniform and luminous that it outshines entire galaxies, briefly becoming the brightest object in the cosmos. These supernovae aren't just fireworks, they're cosmic measuring sticks. Because they always detonate at the same critical mass, their peak brightness is predictable, allowing astronomers to use them as standard candles to map the universe's expansion. It was Type Ia supernova that revealed dark energy's existence, proving the universe isn't just growing, it's accelerating, but the aftermath can be even stranger. If the collapse doesn't completely destroy the white dwarf, it might leave behind an ultra-dense zombie star, a rogue neutron star hurtling through space. Alternatively, if the white dwarf was already packed with heavy elements, the explosion might forge a nebula glittering with gold, platinum, and uranium, scattering precious metals across interstellar space. Chandrasekhar's number isn't just a limit, it's a switch between two cosmic fates. Below it, white dwarfs cool quietly over trillions of years, Above it, they become the universe's most reliable detonations, shaping galaxies and seeding the cosmos with the very elements that make planets and life possible. A reminder that sometimes the finest line separates fading embers from all-consuming fire. If neutron stars are the universe's ultimate pressure cookers, magnetars are their berserker cousins, cosmic monsters wielding magnetic fields so powerful they rewrite the laws of physics. Imagine taking a neutron star's already mind-bending density and cranking its magnetic field up to a quadrillion times stronger than Earth's. That's a magnetar, a stellar remnant where magnetism becomes a force of apocalyptic destruction, capable of ripping atoms apart from thousands of miles away. These magnetic behemoths are born in chaos. When certain massive stars collapse in supernova, their cores don't just compress. They spin at dizzying speeds while their magnetic fields get wound up like cosmic rubber bands. The result is a newborn magnetar, its magnetic energy stored so tightly that even small shifts in its crust trigger cataclysmic starquakes. These quakes aren't like the tremors we know. They're tectonic ruptures on a stellar scale, cracking the magnetar's solid iron surface and releasing bursts of gamma rays so intense they briefly outshine entire galaxies. In 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it ionized Earth's upper atmosphere, despite being halfway across the Milky Way. But the real danger lies in their invisible grip. A magnetar's magnetic field is strong enough to distort the very shape of atoms, stretching them into needle-thin rods. If you could somehow hover within 1,000 miles of one, which you couldn't because you'd already be vaporized, the field would pull the iron from your blood before tearing your molecules apart. Even from light years away, their radiation is lethal. Some theorists suggest that a nearby magnetar eruption could strip a planet's ozone layer in seconds, triggering mass extinctions. Yet these terrifying objects might also be cosmic power grids. Their magnetic fields are so intense they can generate twisted quantum vacuums where virtual particles, normally fleeting fluctuations in empty space, get yanked into reality. Some pulsars once thought to be ordinary neutron stars might actually be dormant magnetars, their magnetic fields slowly decaying over millennia, and when two magnetars collide, the resulting gravitational waves could reveal secrets about quantum physics under conditions no lab could ever recreate. Magnetars remind us that the universe doesn't just push boundaries, it obliterates them. They're proof that even in a cosmos filled with extremes, nature always finds a way to escalate. And somewhere out there, hidden in the dark, these magnetic nightmares are cracking, flaring, and rewriting the rules of reality itself. After exploring the universe's most densely packed objects, let's venture into the opposite extreme cosmic voids, the hauntingly empty regions where matter seems almost afraid to tread. Picture a bubble so vast it could swallow thousands of galaxies, yet inside there's almost nothing. These voids stretch hundreds of millions of light years across, their interiors so sparse that a single atom might occupy a space the size of a football stadium. If neutron stars are cosmic traffic jams, voids are the universe's abandoned highways, lonely expanses where the density dips to less than 1/10 the average of the observable universe. How do these ghostly regions form? The answer lies in the aftermath of the Big Bang. Tiny quantum fluctuations in the early universe's density grew over billions of years, with gravity amplifying the differences. Matter clustered into filaments and nodes the cosmic web, while the spaces between them were left behind, stretched thin by expansion. The largest voids, like the Boötes void, are so unsettlingly empty that astronomers call them supervoids, with fewer than 100 galaxies scattered across a region where there should be thousands. Yet emptiness can be deceptive. Voids aren't perfect vacuums. They contain faint traces of gas, dark matter, and the occasional runaway galaxy ejected from busier cosmic neighborhoods. Even their negative density has gravitational consequences. Light passing through a void loses energy, a phenomenon called the integrated Sachs-Wolf effect, subtly altering the cosmic microwave background's temperature. Some theories suggest voids might be accelerating the universe's expansion, their repulsive gravity pushing walls of galaxies apart like invisible hands. The irony, these barren regions dominate the cosmos. Voids make up over 80% of the universe's volume, with galaxies huddled along their edges like shells on a shoreline. They're the counterbalance to galaxy clusters and black holes, proof that the universe prefers extremes with little room for moderation. Studying voids challenges our assumptions about density and structure. They're cosmic laboratories for testing dark energy's influence, and their growth rates could reveal whether our models of gravity hold true on the largest scales. In the grand tapestry of the cosmos, voids remind us that absence can be as revealing as presence, and that sometimes emptiness speaks the loudest. At the very boundary of what physics can describe lies the Planck density, a number so incomprehensibly large it redefines extremes. Imagine cramming the entire mass of the observable universe into a single atom. Now squeeze it further until even the concept of space begins to shatter. That's the Planck density, 10 to the power of 96 kilograms per cubic meter, a theoretical ceiling where matter stops behaving like matter and the laws of quantum gravity take over. It's the universe's ultimate pressure limit, a regime so extreme that black holes seem tame by comparison. This isn't just abstract math, it's a window into the first fleeting moments of the Big Bang. For a sliver of time so brief it makes a nanosecond seem eternal, just 10 to the minus 43 seconds after creation, the entire cosmos existed at Planck density. Space itself was a seething foam of quantum fluctuations, with energy and gravity locked in a battle so intense that time and distance lost all meaning. Here, the smooth spacetime we know today was a chaotic storm of virtual black holes popping in and out of existence, each distorting reality on microscopic scales. Why does this matter today? Because the Planck density marks the frontier of our understanding. Beyond it, Einstein's relativity and quantum mechanics, the twin pillars of modern physics, collapse into irreconcilable conflict. To grasp what happened at the universe's birth, we'd need a theory of quantum gravity that doesn't yet exist. Some ideas, like loop quantum gravity or string theory, hint at possibilities. Maybe space is woven from tiny atoms of volume, or perhaps extra dimensions curled into invisibility. But for now, Planck density remains a cosmic, here be dragons marker, separating the known from the unknowable. Yet even in its elusiveness, this extreme leaves traces. The cosmic microwave background, the afterglow of the Big Bang, carries faint imprints of those first quantum tremors. Gravitational wave detectors might one day catch echoes from the universe's first Planck second, a whisper from the edge of time itself. And in particle colliders, scientists recreate microcosms of these conditions, hoping to glimpse how spacetime might behave when pushed beyond all limits. The Planck density is more than a number. It's a reminder that the universe began not with a whimper, but with a roar of such unimaginable intensity that even now, 13.8 billion years later, we're still deciphering its echoes. It challenges us to rethink reality's very fabric, proving that sometimes the most profound truths lie just beyond the edge of comprehension. Brown dwarfs are cosmic paradoxes, objects caught in limbo between star and planet, too massive to be mere gas giants but too small to shine like true stars. These failed stars begin their lives much like their stellar siblings, collapsing from clouds of gas and dust, but they never quite gather enough mass to trigger sustained hydrogen fusion in their cores. The result, a dim, cooling object with a density that defies expectations far greater than Jupiter's, yet not quite enough to light the nuclear furnace that defines a star. Picture a ball of gas with 15 to 80 times the mass of Jupiter packed into a volume barely larger. That compression creates densities reaching 70 grams per cubic centimeter, in some cases over 50 times denser than our solar system's largest planet. For comparison, if you could slice into Jupiter, its core might reach a density similar to wet sand, while a brown dwarf's interior would resemble compressed graphite, with matter squeezed into exotic states by the relentless pull of gravity. Yet despite this crushing density, brown dwarfs lack the internal pressure needed to fuse ordinary hydrogen. Instead, some briefly fuse deuterium or heavy hydrogen in short-lived bursts before fading into obscurity. What makes these objects so fascinating is their slow, inevitable fade into darkness. Young brown dwarfs glow a dim red from the heat of their formation, radiating temperatures up to 2000 degrees Celsius. But over hundreds of millions of years, they cool like dying embers, eventually becoming frigid worlds with atmospheres choked by methane and ammonia. Some, like the famous WISE 0856-0725, dip below room temperature, colder than a winter day on Earth. Yet even in their fading, brown dwarfs refuse to be ordinary. Their high density gives them intense gravity, which can generate powerful magnetic fields 1,000 times stronger than Jupiter's. Some emit eerie auroras without a star to energize them, while others harbor swirling storms larger than continents. And their composition, a chaotic mix of gases, metals, and even molten mineral rain, sodium and potassium condensing into liquid droplets that fall through alien skies. These celestial misfits challenge our definitions. Too dense to be planets, too faint to be stars, they occupy a shadowy realm where the rules blur. And their far from rare recent surveys suggest the Milky Way may harbor as many brown dwarfs as regular stars, a hidden population lurking in the dark, rewriting what we thought we knew about the boundaries of cosmic density. Even the densest objects in the universe have their breaking point. For neutron stars, that catastrophic threshold is known as the Oppenheimer-Volkoff limit, the maximum mass these ultra-dense remnants can bear before gravity wins the final battle and they implode into black holes. Named after physicists J. Robert Oppenheimer and George Volkoff, who first calculated it in 1939, this critical number hovers between 2 and 3 times the Sun's mass, a razor's edge where quantum physics and gravity collide in spectacular fashion. What makes this limit so precarious? Inside a neutron star, the crushing weight is balanced by neutron degeneracy pressure, a quantum mechanical force that prevents neutrons from occupying the same state. But push the mass beyond the Oppenheimer-Volkoff threshold, and this resistance shatters. Neutrons themselves collapse into an unfathomable state, possibly dissolving into quarks or triggering an irreversible gravitational freefall. The exact tipping point depends on the star's composition. Some exotic models suggest neutron stars with hyperon-filled cores or quark matter might endure slightly more mass, while rapid rotation could delay collapse by providing centrifugal support. The consequences of crossing this limit are apocalyptic. Within milliseconds, the star's core succumbs, its outer layers crashing inward at nearly light speed as space-time warps beyond recovery. For a brief moment, the dying neutron star might form a quark gluon plasma, a state unseen since the Big Bang before vanishing behind an event horizon, leaving only a black hole as its tombstone. This isn't just theoretical. Astronomers have spotted neutron stars like PSR J0348+0432, which skirts dangerously close to the limit at around 2.01 solar masses, its existence helping refine our models of extreme matter. Why does this matter? The Oppenheimer-Volkoff limit isn't just about stellar death. It's a laboratory for physics we can't replicate on Earth. By studying neutron stars near this boundary, scientists probe the equation of state of ultra-dense matter, testing whether exotic particles or new forces emerge under such extremes. Gravitational wave observatories like LIGO watch for the telltale ripples when two neutron stars merge, sometimes creating a brief, overmassive remnant that teeters on the brink before collapsing. Each event is a cosmic experiment, revealing how matter behaves when pushed to the absolute edge of existence. In the grand cosmic drama, the Oppenheimer-Volkoff limit is both a finale and a gateway, the last stand of degenerate matter before the universe's most enigmatic monsters are born. And every neutron star dancing near this edge is a ticking time bomb, reminding us that in the cosmos, even the mightiest giants walk a tightrope between survival and oblivion. Dark energy is the universe's greatest enigma, a force so elusive it makes dark matter seem straightforward by comparison. Unlike anything else in cosmology, it doesn't clump, emit light, or interact with matter. Instead, it permeates every corner of space with a bizarre property, negative pressure. Picture a stretched rubber band, pull it, and it resists, creating positive pressure. Dark energy does the opposite. As space expands, dark energy's density stays constant, effectively generating more of itself to fill the void. This relentless push is why the universe isn't just expanding, it's accelerating, galaxies fleeing from one another faster with each passing billion years. The numbers are mind-bending. Dark energy's density is shockingly low, about 10 to the power of minus 27 kilograms per cubic meter, or roughly equivalent to a single hydrogen atom spread across a cubic kilometer of space. Yet despite this apparent frailty, it makes up 68% of the universe's total energy content. How? Because unlike matter, whose influence dilutes as space grows, dark energy's repulsive effect scales with volume. The more the universe expands, the more dark energy dominates, like a whisper growing louder in an echoing hall. This negative pressure defies intuition. In Einstein's equations, it appears as the cosmological constant, a term he initially dismissed as his greatest blunder before astronomers discovered acceleration in 1998. Some theories suggest dark energy is the energy of the vacuum itself, quantum fluctuations bubbling in empty space. Others propose dynamical fields, like an invisible cousin to the Higgs boson, evolving over cosmic time. The wildest idea, that dark energy isn't fundamental at all, but a sign our understanding of gravity breaks down on universal scales. The stakes couldn't be higher. If dark energy's strength increases, it could trigger a big rip, tearing apart galaxies, planets, and eventually atoms. If it fades, gravity might reverse expansion, collapsing the cosmos in a big crunch. Or it might simply persist, leaving the universe to cool into eternal darkness. For now, telescopes like Euclid and the Dark Energy Survey map its influence by tracking billions of galaxies, while lab experiments hunt for subtle variations in fundamental constants. Dark energy isn't just a puzzle, it's a mirror held up to our ignorance. In a universe where density usually means crushing gravity, here's a phenomenon where less is more, where emptiness pushes harder than mass. It reminds us that the cosmos still holds mysteries too profound for even our boldest theories to crack. When two neutron stars spiral toward each other in a cosmic dance of doom, they don't just collide, they detonate a kilonova, one of the universe's most spectacular alchemical forges. Picture this: two city-sized stellar corpses, each packing more mass than our sun, whirling around each other hundreds of times per second before smashing together in a cataclysm so violent it sends ripples through the fabric of spacetime itself. The collision's energy breaches the impossible for a fleeting moment. Densities exceed even those of the neutron stars themselves, compressing matter beyond neutron degeneracy and into a realm where protons and electrons dissolve into a seething, ultra-hot quark gluon plasma. It's in this maelstrom that nature performs its most astonishing magic. As the merged object, either a hypermassive neutron star or a newborn black hole, spews jets of material at nearly light speed, the surrounding debris becomes a nuclear reactor unlike any other. Here, rapid neutron capture, or the R process, ensnares free neutrons into atomic nuclei at breakneck speed, forging heavy elements like gold, platinum, and uranium in quantities that dwarf entire mining operations on Earth. A single kilonova can produce hundreds of Earth masses worth of precious metals, scattering them across interstellar space in glowing, radioactive clouds. The first confirmed kilonova, detected in 2017 alongside gravitational wave event GW170817, was a revelation. The aftermath glowed with the signature of freshly minted gold and lanthanides, proving these mergers are the cosmic foundries responsible for most heavy elements in the universe. Your wedding ring, the uranium in nuclear reactors, even the iodine in your body, all were likely born in the fury of neutron star collisions billions of years ago. But the real drama lies in the merger's final moments. As the stars tear each other apart, tidal forces eject filamentary streams of neutron-rich matter, while the core's incomprehensible density, briefly exceeding 10 times nuclear saturation, triggers magnetic fields strong enough to power a quintillion suns. Some models suggest a magnetar might form temporarily, spinning thousands of times per second before collapsing into a black hole. The resulting gamma-ray burst, beamed like a cosmic lighthouse, can outshine every star in the observable universe combined for a few seconds. These events aren't just destructive, they're creative on a galactic scale. Without neutron star mergers, the universe would lack the heavy elements needed to form planets, life, or even the device you're using to watch this video. And thanks to gravitational wave detectors like LIGO and Virgo, we're now eavesdropping on these rare collisions, catching echoes of the universe's most extreme densities in action. Each ripple in spacetime carries secrets about matter pushed beyond any earthly limit, revealing how the cosmos turns catastrophe into creation. Deep within every neutron star, an invisible battle rages, a perfect standoff between the crushing force of gravity and the subatomic rebellion of quantum physics. The Tolman-Oppenheimer-Volkoff equation is the mathematical referee of this cosmic tug-of-war, a master formula that dictates how these stellar corpses can exist without collapsing into black holes. At first glance, it looks deceptively like the equations governing ordinary stars, but hidden within its terms lurk the secrets of matter pushed beyond sanity's edge. Picture a neutron star's core like a skyscraper under construction. Gravity acts as the relentless weight of floors piling higher, while neutron degeneracy pressure, the quantum refusal of particles to be squeezed together, functions as steel beams resisting collapse. The TOV equation quantifies this balance, calculating how pressure must increase with depth to prevent implosion. But here's where things get wild. Unlike Earth's atmosphere where pressure changes gradually, inside a neutron star, density escalates so rapidly that a millimeter downward could mean a billion times more pressure. The equation's genius lies in its adjustments to Einstein's general relativity. Where classical physics treats pressure as a minor player, the TOV version acknowledges that under such extremes, pressure itself generates gravity. This twist creates a feedback loop. More compression increases pressure, which further warps spacetime, requiring even more pressure to stabilize. It's why neutron stars have a strict upper mass limit. Beyond roughly 3 solar masses, no quantum force can counteract this self-reinforcing collapse. To grasp how extreme these numbers are, consider a neutron star's crust. Near the surface, matter is light, merely 1 trillion times denser than water. But dive just a kilometer down, and atomic nuclei dissolve into a neutron superfluid so dense that a single raindrop's worth would outweigh the Great Pyramid. The TOV equation maps this descent into madness, proving that what keeps these objects stable isn't just density, but how that density dances with curvature of space itself. Solving this equation isn't just academic, it's a window into realms we can't recreate. Laboratories on Earth can't compress matter to neutron star densities, so astrophysicists use the TOV solutions as cosmic test tubes. When gravitational wave detectors catch 2 neutron stars merging, the vibrations encode data about the equation's predictions. Each collision is a stress test for our understanding of matter's final defenses against gravity's ultimate victory. Yet mysteries remain. The equation assumes neutrons stay intact, but what if deeper cores transform into quark-gluon plasma or exotic particles? Some solutions suggest hyperon stars with strange matter cores, while others hint at free quarks behaving like superconductors. Every tweak to the TOV parameters opens new possibilities. Somewhere between its elegant lines might lie the key to the universe's most unyielding state of matter. Far from just a theoretical toy, this equation defines the boundary between existence and oblivion for stellar remnants. It whispers that the cosmos isn't just stranger than we imagine, it's stranger than mathematics can currently describe. And every neutron star spinning in the dark is a monument to this perfect, precarious equation, holding the line between star and singularity. Far beyond our solar system, worlds stranger than fiction lurk in the darkness, planets where the very ground beneath your feet would crush you into a diamond-studded pancake. Take 55 Cancri E, a super-Earth orbiting so close to its star that a year lasts just 18 hours. This blistering hellscape doesn't just boast surface temperatures hot enough to vaporize steel. Its core might literally be a gigantic cosmic diamond, forged under pressures that make Earth's core seem as soft as butter. How does a planet turn into a celestial jewel? It starts with carbon. While Earth's core is mostly iron and nickel, some exoplanets form in carbon-rich systems where carbon outweighs oxygen. Under the crushing weight of a super-Earth's gravity, planets up to 10 times more massive than ours carbon atoms get squeezed into crystalline structures, potentially forming diamond layers hundreds of miles thick. 55 Cancri E's density suggests over a third of its mass could be diamond, a treasure trove larger than Earth itself. But diamond planets aren't the only bizarre cores out there. Kepler-10b, a scorching world with a surface of molten lava, packs twice Earth's mass into a ball barely 1.4 times our planet's size. That means its core is likely solid iron, so compressed it's nearing neutron star-level densities. Then there's GJ367b, a sub-Earth with such extreme density that scientists suspect it's almost entirely metal, a cannonball masquerading as a planet. The real shocker, these ultra-dense cores warp the planet's very landscapes. On a diamond world, rivers of liquid carbon might flow beneath diamond-crusted mountains, while iron-rich planets could sport continents of solid metal, their tectonic plates grinding like rusted gears. The pressures are so intense that even hydrogen, the lightest element, gets squeezed into a bizarre metallic form, conducting electricity like copper while shrouding the core in a shimmering, conductive ocean. What creates such extremes? It's all about formation. Planets born close to their stars lose volatile elements like water and gas, leaving behind dense remnants. Others might be the shattered cores of gas giants stripped bare by stellar winds. Some could even be the remains of ancient neutron stars, their material repurposed into planetary form. Whatever their origins, these ultra-dense worlds prove that when it comes to planetary diversity, the universe has a flair for the extravagant, turning what should be science fiction into startling reality. Among the most bizarre relics of the early universe might be primordial black holes, cosmic ghosts that rewrite everything we know about density and scale. Picture an object smaller than an atom, yet packing the mass of an entire mountain. These miniature monsters wouldn't just bend space-time, they'd punch holes right through it, challenging our understanding of gravity itself. Unlike the black holes born from dying stars, primordial black holes could have formed in the first chaotic seconds after the Big Bang, when quantum fluctuations in the infant universe's density became so extreme that pockets of space collapsed directly into singularities. Some might still be lurking in the cosmos today, invisible yet undeniable. What makes them so peculiar is their impossible compactness. A primordial black hole with the mass of Earth would be smaller than a marble. One as heavy as an asteroid could fit inside a single proton. At these scales, the very idea of density loses meaning. Gravity overpowers all other forces, crushing matter beyond any recognizable form. If you could hold one in your hand, which you couldn't since its gravity would rip you apart, it wouldn't look like a black sphere. Quantum effects might make it shimmer like a fuzzball, its event horizon blurred by strings of vibrating energy. The hunt for these relics is anything but straightforward. Too small to accrete noticeable amounts of gas, they'd be nearly undetectable unless they passed right through a star or planet. The resulting vibrations could leave telltale scars, stars with unexplained heat spikes, planets with sudden seismic tremors. Some scientists even speculate that a primordial black hole might have zipped through Earth in prehistoric times, leaving behind a cylindrical trail of superheated rock. Others suggest they could explain dark matter, their collective gravity binding galaxies together without emitting a single photon, but the wildest possibility. Some might still be evaporating. Stephen Hawking famously theorized that black holes slowly lose mass through quantum radiation, and for tiny ones, this process would be explosive. A primordial black hole with the mass of a skyscraper would finally be dissolving today, unleashing a gamma ray burst brighter than a supernova. Telescopes scan the skies for these flashes, hoping to catch the last gasp of a universe's oldest and most secretive inhabitants. Whether they exist or not, primordial black holes force us to confront the extremes of physics. They're proof that density isn't just about how much you can cram into a space, it's about how completely you can erase the space itself. And if we ever find one, it won't just rewrite astronomy textbooks, it'll redefine what we thought was possible. Among the most elusive theoretical objects in the cosmos might be cosmic strings, filaments of pure spacetime curvature left over from the universe's violent infancy. Picture a crack frozen in ice, but instead of water, it's a flaw in the very fabric of reality itself, thinner than a proton yet stretching across billions of light years. These hypothetical relics would be so dense that just a single inch of string could outweigh an entire mountain range, packing mass into a one-dimensional line where the laws of physics warp beyond recognition. How could such bizarre objects form? In the first fractions of a second after the Big Bang, the universe underwent a series of phase transitions, like water freezing into ice but on a cosmic scale. If these transitions weren't perfectly smooth, defects might have formed, much like cracks appearing in cooling glass. Cosmic strings would be the most dramatic of these defects, regions where spacetime itself pinches into an infinitely thin, unimaginably dense thread. Unlike black holes, which curve spacetime into a pit, strings would bend it like the edge of a razor, creating permanent gravitational scars across the cosmos. Their presence would rewrite gravity's rules. A cosmic string passing through a star would distort its light into twin images, a phenomenon called gravitational lensing, but with a twist. Because strings are perfectly straight, the effect wouldn't be the usual smeared arcs we see from galaxies or black holes. Instead, it would produce mirror-like duplicates, crisp and abrupt, as if the universe itself had a glitch. Even more unsettling, if a string swept through a planet, the space on either side would shift instantaneously, effectively teleporting everything apart without any warning. But the wildest implication, cosmic strings might still be vibrating. Models suggest these filaments wouldn't lie still. They'd whip through space at nearly light speed, creating ripples in spacetime so powerful they could shake entire galaxies. Some theories even link them to fast radio bursts, those mysterious cosmic signals that arrive without explanation. And if two strings crossed, the collision might release enough energy to briefly outshine a supernova, or worse, form a black hole from pure geometry. The hunt for these spacetime scars is ongoing. Astronomers scour telescope data for strange lensing patterns or unexplained gravitational waves. Others search for their fingerprints in the cosmic microwave background, where a string's passage would leave faint, linear temperature variations. So far, no definitive evidence has emerged, but their potential existence keeps theorists captivated. After all, if cosmic strings are real, they'd be the ultimate cosmic fossils, a snapshot of the universe when it was barely a heartbeat old, frozen in threads of pure density that defy time itself. If you could zoom out far enough to see the universe on its grandest scale, you wouldn't find chaos. You'd discover an intricate cosmic spiderweb, glowing with galaxies strung along shimmering filaments like dew on a morning cobweb. This is the cosmic web, the universe's largest and most elegant structure, where density dictates the architecture of reality itself. These filaments, threads of dark matter and gas stretching hundreds of millions of light years, form a labyrinthine network, with galaxies huddled at their intersections like glittering cities at crossroads, while the voids between them stretch into deserts of near-nothingness. The cosmic web's blueprint was drawn in the first moments after the Big Bang, when quantum ripples in the infant universe's density grew under gravity's relentless pull. Over billions of years, dark matter, the invisible scaffolding of the cosmos, clumped first, its gravitational tendrils funneling ordinary matter into rivers of gas. Where these currents intersected, galaxies blossomed, creating the web's luminous nodes. The densest clusters, like the Laniakea supercluster our Milky Way calls home, anchor vast regions of space, while filaments like the Pisces Cetus supercluster complex weave through the voids, connecting galactic metropolises across unfathomable distances. What's staggering is how perfectly emptiness and density balance here. The filaments themselves are hardly solid. Their gas averages just 10 atoms per cubic meter, a vacuum by Earth standards. Yet contrast that with the nodes, where thousands of galaxies crowd together so tightly their gravity distorts space-time into funhouse mirrors, bending light from more distant objects into arcs and rings. The densest known node, the El Gordo cluster, packs the mass of 3 quadrillion suns into a region just 10 million light-years across, its core so packed that galaxies collide like frenzied commuters in a cosmic subway. This web isn't static, it pulses with movement, galaxies flowing along filaments toward nodes in a process called galactic accretion, like water droplets sliding down a spider's silk. Some galaxies race at thousands of kilometers per second, caught in the web's gravitational currents. Meanwhile, the voids expand, their repulsive gravity a side effect of dark energy, pushing the filaments further apart over time. Telescopes like the Dark Energy Survey map these flows in exquisite detail, revealing how the web's structure encodes the universe's expansion history. But the true magic lies in the web's invisibility. Over 80% of its mass is dark matter, detectable only by how it warps light from background galaxies. The rest is largely ionized gas, so hot it glows in X-rays rather than visible light. To truly see the cosmic web, astronomers must combine observations across the electromagnetic spectrum, stitching together radio waves, infrared, and X-rays into a single tapestry. New tools like the James Webb Space Telescope peer even deeper, spotting faint galaxies along faint filaments, tracing the web's skeleton into the ancient universe. This grand structure isn't just a pretty pattern, it's the universe's way of organizing itself. Without the web's filaments funneling gas, galaxies would lack the fuel to form stars. Without nodes, matter would scatter too thinly for superclusters to emerge. And without voids, the web would lose its contrast, collapsing into a featureless fog. Every time you gaze at the night sky, remember, you're not just seeing stars, you're glimpsing a single thread in the universe's most magnificent tapestry, woven from the interplay of density and emptiness across 13.8 billion years. Black holes might seem like the ultimate cosmic dead ends, places where matter and energy disappear forever. But thanks to a groundbreaking discovery by Stephen Hawking, we now know even these gravitational monsters have an expiration date. It all comes down to a bizarre quantum quirk called Hawking radiation, a process where black holes slowly leak energy, shrinking over unimaginable timescales until they vanish in a final explosive burst. The magic happens right at the event horizon, where gravity's grip is so strong that not even light can escape. quantum physics tells us that empty space isn't truly empty. It's a seething foam of virtual particles, popping in and out of existence in particle-antiparticle pairs. Normally, these pairs annihilate almost instantly, but near a black hole's edge, something extraordinary occurs. If one particle falls in while the other escapes, the black hole effectively loses energy and therefore mass over time. The escaping particles carry away tiny bits of the black hole's essence, like a slow, inevitable evaporation. The numbers are staggering. A black hole with the mass of our Sun would take 10 to the power of 67 years to fully evaporate, a time span so vast it dwarfs the current age of the universe. But smaller black holes, they're on a much faster timer. A black hole weighing just 1 million tons, the size of a mountain, would blaze through its energy in less than a second, ending its life in a gamma ray burst brighter than a supernova. These explosions might be the universe's way of erasing its tiniest mistakes. What's truly mind-bending is the temperature. Hawking radiation implies black holes aren't cold, they're faintly warm, emitting heat inversely proportional to their size. A supermassive black hole might be colder than the cosmic microwave background, barely radiating at all, while a microscopic one would be hotter than a star's core, boiling away furiously. This revelation reshapes our understanding of cosmic endings. If black holes can fade, then nothing in the universe is truly permanent, not even the darkest, most voracious pits of gravity. And somewhere out there in the distant future, the last black hole will flicker out, leaving behind only a whisper of radiation as its final farewell. They slip through your body by the trillions every second, ghostly particles so insubstantial they barely interact with matter at all. Neutrinos are the universe's ultimate specters, born in the hearts of stars, the fury of supernova, and even the decay of atoms in Earth's crust. Nearly massless and devoid of electric charge, these phantoms traverse planets like their empty space, making them astronomically difficult to detect. Yet despite their elusive nature, neutrinos may hold a startling secret. Collectively, their sheer numbers could shape the cosmos itself. Consider the scale. For every proton in the universe, there are roughly 1 billion neutrinos. The Sun alone blasts out 65 billion of them per square centimeter every second, a relentless torrent that has continued for billions of years. Supernova up the ante. When a star explodes, 99% of its energy radiates as neutrinos, a fleeting burst so intense it could outshine all the stars in the observable universe combined. Even mundane processes like potassium decay in bananas produce these particles, yet pinning one down demands Herculean effort. Detectors like Japan's supercamioc and a tank filled with 50,000 tons of ultra-pure water might catch just a handful per day after filtering out cosmic noise. Here's the twist: neutrinos aren't entirely massless. In the 1990s, experiments proved they oscillate, changing flavors between electron, muon, and tau types as they travel. This behavior confirmed they must have some mass, however minuscule. Current estimates suggest a single neutrino weighs less than 1/millionth of an electron, but multiply that by the countless trillions drifting through space, and their combined gravitational influence adds up. Across billions of light-years, this neutrino background could subtly steer galaxy clusters and sculpt the cosmic web's faintest threads. Their ghostly heft challenges our understanding of density. Unlike black holes or neutron stars, where matter is crammed into microscopic volumes, neutrinos represent the opposite extreme, a whisper-thin haze stretching across the entire universe. Yet in aggregate, their mass might rival all the visible stars combined. Some theories even suggest relic neutrinos from the Big Bang, now cooled to near absolute zero, form an invisible ocean permeating everything. If we could scoop up a cubic light-year of space, its neutrino content might outweigh Mount Everest. This raises profound questions. Could neutrinos be part of dark matter's mystery? Probably not. They move too fast to clump like dark matter seems to. but their mass still tweaks the universe's expansion rate. Future detectors, like the Deep Underground Neutrino experiment, aim to measure their weight with precision, potentially revealing why the cosmos leans the way it does. For now, these phantoms continue their silent dance through stars, planets, and you're reminding us that density isn't just about crushing matter. Sometimes it's about the faintest touches accumulating across eternity. At the heart of our Milky Way lies a cosmic storm, a swirling maelstrom where stars jostle for space like commuters in a rush-hour subway. The galactic center packs over 10 million stars into a region just a few light-years across, a density so extreme that if Earth orbited here, our night sky would blaze with thousands of stars brighter than the full moon. This isn't just a crowded neighborhood, it's a gravitational pressure cooker where stellar orbits whip around at thousands of kilometers per second, bent into wild loops by the combined pull of visible stars, dark matter, and the supermassive black hole Sagittarius, a star lurking at the core. The numbers defy intuition. Within 1 light-year of Sagittarius, a star, stars are packed 20 million times more tightly than in our solar system's vicinity. Some, like the hypervelocity star S2, slingshot around the black hole at nearly 3% light speed, completing an orbit in just 15 years. Others, like the mysterious G objects, appear to be gas clouds masquerading as stars, perhaps the shredded remains of disrupted planets or failed binary systems. And between them, a graveyard of smaller black holes, dozens or even hundreds, dragged inward over eons to form a sinister swarm around their supermassive monarch. What creates this urban sprawl of celestial bodies? The Milky Way's core is a relic of violent mergers, smaller galaxies consumed over billions of years, their stars herded toward the center by dynamical friction. Dark matter plays its part too, its invisible halo concentrating here like syrup pooling at the bottom of a glass. The result is a region where star formation defies normal rules. Typically, giant molecular clouds need millions of years to collapse into stars. Near Sagittarius, a star, gravity works overtime, compressing gas into protostars at breakneck speed. Some newborn stars here shouldn't exist. The black hole's tides ought to rip apart nurseries before they ignite. Yet they burn defiantly, their very presence challenging our models of stellar birth. The chaos isn't just gravitational, it's electromagnetic. Swirling magnetic fields channel particles into jets, while shock waves from colliding gas clouds glow in X-rays. Infrared telescopes pierce the dust to reveal young, massive stars that somehow formed in this hostile environment, their blue-white brilliance standing out against the older, yellower crowd. And threading through it all are filaments of ionized gas, strung like cosmic spider silk for dozens of light years, their origins still debated. Could they be scars from past black hole outbursts or the wakes of stars plowing through interstellar material? Yet for all its violence, the galactic center is oddly quiet. Sagittarius, a star, is a sleeping giant, its current feeble emissions a far cry from the quasar-like fury it may have unleashed in the past. This calm might be temporary. Astronomers have spotted gas clouds like G2 approaching dangerously close, their potential disruption possibly feeding the beast in years to come. When that happens, the Milky Way's core could awaken in a blaze of radiation, visible across the universe. Studying this crowded nucleus isn't just about mapping our home galaxy, it's a window into how all galaxies evolve. Every star here, every black hole, every ripple of magnetic field tells a story of cosmic forces pushed to their limits. And somewhere in that frenzy, hidden by dust and distance, lies the answer to why galaxies like ours look the way they do, their hearts as dense and dynamic as the universe itself. Some of the most violent particle accelerators in the universe don't come from human engineering. They erupt from the hearts of galaxies where black holes launch relativistic jets into the void at nearly the speed of light. Picture a beam of plasma stretching millions of light years, so finely focused it could drill through cosmic distances without spreading, packing enough energy to outshine entire galaxies combined. These aren't just cosmic fireworks, they're the universe's ultimate power lines, fueled by the most extreme densities and temperatures imaginable. The engine behind these jets is pure chaos. Supermassive black holes like the one powering Quasars, R345, don't just swallow matter, they shred it into a swirling accretion disk, heating gas to billions of degrees until it glows brighter than a trillion suns. But not all that material falls in. Magnetic fields twisted by the black hole's spin channel some particles outward along the poles, accelerating them to 99.9% light speed in a process we still don't fully understand. The result, twin beams of plasma so dense with energy that a single teaspoon's worth would require all the nuclear power plants on Earth running for a century to match its output. What makes these jets truly bizarre is how they maintain their razor-thin focus across cosmic distances. Unlike a flashlight beam that scatters, relativistic jets stay collimated for millions of light years. Some, like those from galaxy M87, stretch over 5,000 times longer than the Milky Way's diameter. This unnatural focus comes from the jet's internal structure, a superheated core of electrons and protons wrapped in a sheath of magnetic coils that act like a cosmic waveguide, preventing dispersion. The particles inside don't just move fast, they're denser than a neutron star's crust, packed so tightly their collective energy warps spacetime around the beam itself. The numbers defy belief. A typical jet from an active galactic nucleus carries kinetic energy equivalent to converting the mass of 1,000 suns directly into pure motion every second. When these beams slam into intergalactic gas, they create shock waves visible in radio telescopes, glowing lobes that can span entire galaxy clusters. Some, like the infamous Death Star Galaxy 10934848, even use their jets as weapons, punching holes through neighboring galaxies, stripping them of star-forming gas in a cosmic assault. Yet these jets aren't just destroyers, they're architects. By heating surrounding gas, they regulate galaxy growth, preventing runaway star formation that would burn out cosmic neighborhoods too quickly. They might even seed the universe with heavy elements, their particle impacts forging gold and uranium in interstellar space, and when two jets collide. The resulting particle showers could produce neutrinos, ghostly particles now being hunted by detectors like Ice Cube at the South Pole, the most unsettling part. We're seeing these jets in slow motion. Due to relativistic effects, particles moving toward us appear thousands of times brighter than those drifting sideways, an illusion called Doppler boosting. Some blazars jets pointed directly at Earth flicker in brightness over days, despite originating from regions light years wide. This time-warping trick means we're witnessing a cosmic mirage where the laws of physics conspire to make the impossible visible. Relativistic jets remind us that black holes aren't just gaping mouths, they're also cosmic blowtorches, sculpting the universe with beams of pure energy. Every time one flares up, it writes its signature across the cosmos in letters of plasma and radiation, a reminder that even in the darkest voids, creation and destruction dance on a knife's edge. Zoom out far enough, and the cosmos reveals one of its greatest ironies, a universe filled with unfathomably dense objects like neutron stars and black holes. Yet on the grandest scale, it's almost embarrassingly empty. Take the entire observable universe, the Hubble volume, a sphere 93 billion light-years across containing 2 trillion galaxies, uncountable stars, and all the dark matter and energy we can't even see. And if you calculate its average density, you're left with a figure so low it defies intuition, roughly 9.9 times 10 to the power of -30 grams per cubic centimeter. That's equivalent to just 5 hydrogen atoms floating in a space the size of your bedroom. This number seems impossible when contrasted with the extremes we've explored. A neutron star's core is a staggering 10 to the 15 times denser than this cosmic average, while the singularity inside a black hole is so compressed it makes neutron stars look as sparse as interstellar space. Yet here's the twist. The universe's overall density is dominated not by galaxies or stars, but by voids, those vast, nearly empty regions stretching hundreds of millions of light-years between filaments of the cosmic web. In fact, if you smoothed out all the matter evenly, each cubic meter of space would contain only about 1 proton's worth of mass. That's the definition of a hard vacuum on Earth, but it's the default setting for the cosmos. How does this paradox hold? It's all about distribution. Imagine dumping a handful of sand into an Olympic-sized swimming pool. The grains might clump in certain spots, forming dense little islands, but the pool as a whole would still be overwhelmingly water. The universe works the same way. Its matter huddles in galaxies and clusters, while the rest is a near-perfect void. Even within galaxies, density varies wildly. Earth orbits in one of the Milky Way's sparser regions, where stars average about 1 per 4 cubic light-years. But venture into a globular cluster like Omega Centauri, and you'd find 10,000 stars crammed into the same volume, a density spike 100 million times above the cosmic mean. Dark matter and energy add another layer to this puzzle. Though invisible, they make up 95% of the universe's total energy density, with dark energy's repulsive effect accelerating expansion and stretching matter ever thinner. Yet in regions like galaxy clusters, dark matter's gravity piles visible matter into dazzlingly dense knots, creating islands of extreme density in an otherwise sparse sea. The takeaway: density depends entirely on scale. Zoom in close enough and you'll find matter packed to the breaking point inside stellar remnants. Zoom out and the universe becomes a study in emptiness, a lesson that nature's true extremes aren't just about how much you can cram into a space, but how cleverly it arranges itself across the grandest canvas of all. Imagine a clock ticking slower on a spaceship orbiting a black hole than on Earth, not because it's broken, but because time itself has stretched like taffy near the black hole's crushing gravity. This isn't science fiction, it's gravitational time dilation, one of the universe's most mind-bending consequences of extreme density. Near a black hole's event horizon, where matter is packed so tightly that escape requires faster than light speed, time doesn't just slow down, it grinds to a near standstill from an outsider's perspective. The movie Interstellar brought this phenomenon to life with Miller's Planet, where every hour spent on its surface cost the crew 7 years back on their ship. While the numbers were exaggerated for drama, the physics behind it is shockingly real. Einstein's general relativity reveals why. Massive objects warp spacetime like a bowling ball sinking into a trampoline, and the deeper the warp, the slower time flows. Near a black hole, this distortion becomes so severe that time dilation reaches extremes no lab on Earth could replicate. If you could hover just outside the event horizon of a stellar mass black hole, let's say, where gravity is 1,000 times stronger than Earth's, a single minute for you might stretch into years for someone watching from a safe distance. Your heartbeat, your breath, even the flicker of your eyelids would appear frozen in slow motion to an outside observer. This isn't just theoretical. Astronomers have observed time dilation in our own galaxy. The stars whipping around Sagittarius, a star, the Milky Way's supermassive black hole, show subtle shifts in their light's frequency as they navigate the beast's gravitational grip, proof that their clocks tick measurably slower than ours. Even Earth's gravity creates a tiny time dilation effect. GPS satellites must adjust their clocks daily to account for the fact that time moves faster for them in orbit than on the planet's surface. But near a black hole, the effect isn't just measurable, it's catastrophic. Here's where it gets stranger. Time dilation isn't just a one-way street. From your perspective hovering near the black hole, time elsewhere would appear to speed up. Watch a distant star's life cycle through a telescope, and you might see its entire evolution play out in what feels like days. This asymmetry creates a paradox. If you fell into a black hole, an observer would see you freeze at the event horizon, slowly reddening as your light stretches into invisibility. But for you, time would feel normal right up until the moment tidal forces tore you apart. The implications are staggering. If humans ever venture near black holes, they'd return to a universe that's aged centuries without them. Entire civilizations could rise and fall in what feels like a brief expedition. And for astronomers, this time warp isn't just a curiosity, it's a tool. By studying how light bends and slows near these cosmic monsters, we can map their gravity with precision, testing relativity's limits. Black holes don't just warp space, they twist time into knots, proving that density doesn't just crush matter. It rewrites the very rules of existence, turning the universe's most fundamental constant into a variable plaything of gravity. And somewhere out there, in the dark, time itself is crawling to a halt at the edge of oblivion. The universe's grand finale hinges on a cosmic tug of war between two unstoppable forces: the relentless expansion driven by dark energy and the patient, persistent pull of gravity. Scientists call this the ultimate density dilemma. Will the cosmos thin out into eternal darkness or collapse back into a fireball? Both scenarios are rooted in the same question: how much stuff is really out there, and how will its density shape the fate of everything? Picture two possible endings. In the first, dark energy wins. Galaxies accelerate apart until their light can no longer reach us. Stars burn out, and black holes evaporate via Hawking radiation over incomprehensible eons. The universe reaches a state of maximum entropy, what physicists call heat death. Here, density isn't just low, it's non-existent. Particles become so spread out that temperatures approach absolute zero, and space itself becomes a vast, silent graveyard where even time loses meaning. This isn't a dramatic explosion or implosion. It's a slow, quiet fading, like embers cooling in an endless void. But there's another possibility, one where gravity fights back. If the universe's total density, including dark matter and energy, exceeds a critical threshold, expansion could reverse. Galaxies would begin rushing toward one another, collisions reigniting star formation in a brilliant but short-lived renaissance. Eventually, everything, planets, stars, even space-time itself, would crumple into a singularity hotter and denser than the Big Bang. This big crunch would mirror the universe's birth, with all matter compressed into a point of infinite density. Some theories even suggest this could trigger a new Big Bang, birthing another cosmos in an endless cycle of expansion and collapse. The verdict: current evidence leans toward heat death. Measurements of the cosmic microwave background and distant supernova suggest dark energy's repulsive force is accelerating expansion, not slowing it. The universe's density appears too low for gravity to ever regain dominance, but mysteries remain. Dark energy's nature is still unknown. Could its strength change over time? If it weakens, gravity might yet stage a comeback. Alternatively, if dark energy grows stronger, it could tear apart galaxies, stars, and even atoms in a big rip long before heat death arrives. These aren't just abstract thought experiments. The answer shapes how we understand time, entropy, and the very arrow of existence. Will the universe end in icy solitude or fiery rebirth? For now, the cosmos keeps its secrets, but every telescope, every particle detector, and every equation brings us closer to glimpsing the final act of this epic story. And in that uncertainty lies a profound truth. The fate of the universe isn't written in stone. It's written in density. From neutron stars where a teaspoon of matter outweighs mountains, to black holes so dense they trap light itself, we've journeyed through 30 astonishing extremes where the universe defies all intuition. These cosmic heavyweights aren't just curiosities. They're the architects of reality, forging elements in supernova, bending space-time with their gravity, and even shaping the fate of galaxies. Think about it. Without the crushing densities inside collapsing stars, gold and uranium would never exist. Without the void's eerie emptiness, the cosmic web couldn't weave its glittering strands. Every extreme we've explored, from quark stars to relativistic jets, reveals a universe that thrives on contrast. where density isn't just a number but a force that births, destroys, and transforms. Consider how these titans touch our own existence. The iron in your blood, forged in a dying star's core. The energy powering your devices, traced back to the sun's ultra-dense furnace. Even the atoms in your body carry echoes of the Big Bang's quark-gluon plasma, a density so extreme it vanished in microseconds. These aren't distant phenomena, they're the reason you're here, the reason planets orbit, and the reason the night sky holds more than darkness. So, which fact left you breathless? Was it the magnetars' starquakes powerful enough to ripple Earth's atmosphere from halfway across the galaxy? Or the cosmic string's hypothetical flaws in space-time that could slice through planets like a knife? Maybe it was the eerie quiet of supervoids, where emptiness stretches farther than our minds can grasp. Drop a comment below and share the moment that rewired your brain. And if you're craving more mind-bending journeys through the cosmos, hit subscribe. We've only scratched the surface of the universe's deepest mysteries. The next discovery might just shatter everything we thought we knew.